Hi guys, welcome back to my YouTube channel. Today we'll be dealing with the load extension graph, which is the tensing test carrying out from the milled steel piece. Right. So so this is example 2.3 stress. This is N5 stress of material. So if you have not subscribed to my YouTube channel, please may you kindly subscribe and click that notification button so that you'll be notified whenever I post some new video there. Example 2.3 says the following figure gives the detail of a tensile test carried out on a mild steel piece with the diameter is the one that will use. This is original diameter, and 250 length is the one that will use its original length between the gauge point. The one that you have given in the statement, it is the original one. So about that, between the gauge point. So this is what we have there: a load and extensions. Load and extension. Remember, this is continuing. It's not like we've given two different things. It's just that they had no enough space. So this thing contains like this. Contains, it's a continuity. Will contain is one and the same thing. So guys, this is what we have: load and extension. So in the if the change in cross-sectional area is so small that does not need to be taken account in the earlier part of the test, plot the load extension curve and determine the following. We should plot, and then we should determine the following. A, there we should determine modulus of elasticity, yield stress, ultimate stress, percentage elongation, the allowable working stress there. So we have to plot, guys. To plot, let me check what can I use here. Let me check the size there. Let me check. Okay. Okay, it's fine. We should plot. This is what we are given. 0.1, 0 goes with 0, 0.9. You see here there is 0, 0, 0, 0, 0, 0, 0, 0, until here we get to 0, 1, 2, 1, 1, 1, 1, 1, 2, 3. I'll just go by 0, 1, 2, 3, 4, 5. Finish and clear. Here we have 50, 50, 100, 150. I'll just go by 50s so that I won't waste no time there. Then I will plot our thing there. So what you must know, here we'll have extension, but okay, let me first, won't be exactly up to scale. I'll just do my things here. Here we'll say 1, then here maybe I have 2, somewhere here maybe I have 3, there 4, there 5. So goes there again, can say 50, 100, 150 there, okay, say 50, then can say 50, 100, 150, 200, 200, 250 here, there. So can have 50 there, 100, 150, 200, 150 there. Why I say 150, 250 is 200, 250, yeah. And then we had, remember, here we'll have load on our y-axis. This is a load and will be in kilonewton. Here we'll simply have, can say 1, 2, 3, 4, 5. Let me zoom in. So here, guys, this is 1, this is 2, can say 1, 2, 3, 4, 5. Then this is the extension. This will be the extension. Is in millimeter, right? So you can try and plot. First point is 0.09, goes with 50. Then me shows here a point. This is a middle. That is, yeah. What is this? Shape that goes with 50. Somewhere here, 0.09 is 0.0 something. I can say somewhere here. Can say somewhere there. Then if I can go upwards there, then there I will have make a dot. We have 3 dots, then 100 goes with 0.9, 150 goes with that, go 100, 0.0 is close to somewhere here. It's 0.02. I can see somewhere here. Right. Yeah. Then This is another value 1620,03. Just goes like that, somewhere there. Is exhausting, this thing. Go to that point 150 right here, 170, goes like that. It's exhausting, blind. So go there, somewhere there. Go again somewhere there. 170 and 180, they are closely related. As you can see, this point are packed closely there. 170 somewhere there. This point is there. They are in 180 somewhere. Yeah. Yeah, we have the points. So we'll have something like this of this niche. So yeah, this is how your graph will look like if you have plotted occurrence. Guys, as you can see, this thing is very long. Just put it, this is the estimation, and not properly like that. So yeah, your graph will be something like this. Right, then if you like, you can draw your test up, but there's no need. You can draw your test piece. They like to give you it's a waste of time. There's no, don't draw that way test piece. So this is what you have, guys. This is the graph. So question A, the modulus of elasticity. A, we want the modulus of elasticity. If you are given this is equal to force multiplied by length over area multiplied by x, and then this is original. So what is original area? What will be the original area? Original area will be pi over 4 d squared, whereby we'll use the test piece. What is tested? The one that you've given of the test piece. Here it is. Diameter is what? 30 divided by 100. That will be by 1000 with 0.03. Your squared is your area, original one, 706,858 times 10 to the minus 6 meters squared. Yeah, this is what we'll have. Now we have the area. The length we know it was 250. The one you've given will be 0.25 meter. The original one of the test piece here. We're using the original. So yeah, E will be equal to the force there. The force must be, take any force between, find the force, remember, between the line where it is straight, between here, this point, between the proportional lead. It's where you will find your, can take any, the value of force. You can take 100 or 1 or 50, is up to you, but must correspond with what you know. So I can take 150 because it's clearly there. If I say 150, remember it's in kilonewtons, times correspond with 0.25, as we know. That is original length multiplied by original area times 10 to the minus 6 times, what is this? Change in length. Change in length is the one in the test piece, 150. Here's the change in length, 0.9 but millimeter there. So that will be meter, will be 0.19 times 10 to the minus 3. So E, if you punch this, get Young modulus will be 186,146 gigapascal. This is what you have. And then what is B? We're looking for yield point. Yield point, we determine the yield point is where the length becomes long. The length becomes long is between somewhere. Yeah, somewhere there. Somewhere here. The long, yeah. I can say 1/6 or what, will depend. There's a range. You can take any there that you see. Yield point is equals to, obviously I've given the force, the yield point must correspond over area, but it's original always. So at the yield, if I can take this, multiply by, okay, 100 is not at the yield. Let me say 100 is not at the yield. 160, yeah, somewhere here. Remember the yield. There is a limiting of proportion. The yield must be somewhere here. Yeah, that is yield, somewhere there. As you can see, somewhere. Yeah, the force will be between somewhere there. You'll see between that. I will just say 60 times 10 to the power of 3 divided by the original area. If we punch this, that yield will be equals to right 226,354 megapascal. Then C, we should calculate what the ultimate, yeah, the ultimate, we'll calculate ultimate after the percentage elongation after this. Okay, ultimate is at the highest. Ultimate will be equals to force ultimate, we know, divided by A, the original one. Highest point, here's the highest point, somewhere there. Highest point there. 1 second, say 154 or what, or 254, 56, I don't know, 254 or 56, yeah, somewhere there. Multiply by, obviously it's in kilonewton, over the original area. We've calculated it, which is 706,858 times 10 minus 3. Then this, if you punch this on your calculator, ultimate is 360,751 megapascal. Then D, it was a percentage elongation. We know the formula. Original length multiplied by 100. I will use this actual change in length. That here, there is the change in length. Then the original is the one. We'll use that thing there, which is, but it's in millimeter, isn't it? So yeah, 0.93, but also even 250 is in millimeter. You know, there's no need. If it's like this, it's fine. SI units will cancel, so there's no need to convert. Multiply by 100. So the percentage elongation, 1,972%. So E, allowable tension, we said we should calculate allowable tension. We know that it's a working which is called, so it's allowable what allowable working stress with a factor of safety of 2 for the yield stress. Okay, for the yield, so here we have yield factor of safety. Yield, we have calculated the yield. Where was the yield? Is this? We'll take that value, which is 226,354. The safety factor, it was 2. This would be 1113,177 megapascal. So this is what it is, guys. So thank you guys for watching. Please do not forget to subscribe to my YouTube channel.